Alright, hello class. Today we're looking at power series. And they actually sound a bit cooler than they really are. All a power series really is a series that we put x's into. So we now create a function with a series, right? So f of x equals a series with, say, k going from, it could be 0 to infinity, some constant, and some x to the k. Okay, so it's basically a polynomial that we take out forever. So these aren't quite Taylor series yet. These are just going to be general power series. So they're series of pretty much this form where we essentially are looking at infinite degree polynomials. Okay, so basically polynomials with degree going to infinity. Okay, so here's the more general definition of a power series. I mean, it is essentially a series with x's in it. So this is the power series centered at A. Right, so here's the center. And here are the coefficients ck. Okay, and there are the thing that makes power series sort of tricky is that they will converge for different values of x. So if we put a 1 in here, it might converge, but if we put a 10, it may not, because you can kind of see that if, say, the c were gone, it was just x to the k. Well, x to the k would be a geometric series. So the base example I like to use is, imagine k going from 0 to infinity of just x to the k. Well, this is a geometric series. Right, which will converge for all x's where the absolute value of x is less than 1, and diverge for the absolute value of x greater than or equal to 1. All right, so in this particular example, and it's the example I like to use because we've already kind of looked at this just with r instead of x, but we could always make this a function, like just call this f of x, and then get a new series for each x. Okay, so when x, absolute value of x, is strictly less than 1, this means f of x converges on the interval -1 to 1, because absolute value of x less than 1 means that x is trapped between -1 and 1. So it's on the open interval -1 to 1. Okay, this is called the interval of convergence. And that's actually an official term that gets its own definition and everything. The distance between the center which in this case is 0, and the boundary is the radius of convergence. Now it may seem weird to call this the radius of convergence when we're not really talking about a circle, but the thing to understand here is a lot of results for series are done in, imagine a two-dimensional space, and instead of convergence being on just a line, it will actually be on a circle. Okay, so that's where a lot of the results were first established, and when they moved them back here to just the real line, the name stuck. So here, the radius of convergence, which we call capital R, is 1. It's essentially half the interval. Okay, half the length of the interval, essentially. Okay, so in this case, R is 1. So the radius of convergence is 1. The interval of convergence is -1 to 1. Okay, outside of this interval, this series will diverge. Okay, so there are a couple of ways that a general power series can behave. Okay, so the general power series, f of x equals, the series k going from 0 to infinity, c of k times x minus a all raised to the k, it can converge in a number of ways. All right, so the first way that a power series can behave is it just converges everywhere. Converges for all x, and so any x you throw into it, it will converge, and that makes its radius of convergence infinity. Okay, yeah, we do say that r equals infinity in this case. All right, so that's the nicest series you could get, is that any x you throw at it, it converges just fine. All right, the second possibility is that f converges on an interval around a, and it's always going to be, its interval of convergence is a minus r to a plus r. So if we look at this on a number line, if a is here, if we have a case like this, we will always have a balanced interval around a where the length from a to the outside boundary is the radius of convergence. Okay, so that it will always happen that way. If it doesn't converge everywhere, then it will converge on a nice balanced interval around the center. Okay, there's a reason it's called the center, a reason it's called the radius, is because it's nice and balanced that way. Okay, now it doesn't have to be, say 0 could be right here and this could be negative and positive, but it's always going to be this nice balanced interval. All right, and this comes from basically x minus a being less than r, and f diverges for x minus a greater than r, and it's inconclusive. We have to check. More work is required to see what is happening on the endpoints. And F's behavior on the endpoints could go either way. And F can converge or diverge. On the endpoints. Right, so at the actual a minus r and a plus r, we could get convergence there, or we might not. Okay, so we'll see some cases where we get, either or situations coming up. All right, and then it could only converge at the center. right? So that would mean that the series basically just converges here at A, diverges everywhere else. Okay, so here the interval of convergence is literally just the element A, and the radius of convergence here is 0. So the radius of convergence can go range from anywhere between infinity to 0. Okay, if it's infinity, the interval of convergence is the entire real line. If r is 0, then the interval of convergence is literally just a single value, and anywhere in between we get a nice balanced interval of convergence. All right, so a natural question here is, well, how do we find I and R? How do we know which case it's going to be? And the answer is really we use the ratio or root test as, deemed necessary. Now I could describe this and write it out in words, give you a little algorithm, but honestly, I think it's just easier to see it in action. So let's take a look at an example. All right, so we'll start with a fairly straightforward example here. We'll look at the series from k going from 0 to infinity of x to the k all over k factorial. And maybe I should rewrite my k here so it looks a little less like an x. From the last video, you may recognize this pattern as the e to the x Taylor polynomial. And it turns out that this is the Taylor series from e to the x. So how we use the ratio and root tests? Well, in this case, since I see a k factorial, I'm going to want to use the ratio test. Okay, so the ratio test, remember we look at r, and that's going to be the limit as k goes to infinity, the absolute value of, remember, it's the k plus 1 term. So I have x to the k plus 1 all over k plus 1 factorial. Right? Then times the reciprocal. So we're going to flip the kth term over. So it'll be k factorial over x to the k. All right, so let's simplify this down a little bit. One thing to keep in mind here is, well, the factorial is always going to be positive, and we can move the absolute value in around the x's. So this will be the limit as k goes to infinity of the absolute value of x to the k times the absolute value of x. So that's how we split this up. This will be k plus 1 times k factorial. This here will simplify to k factorial over the absolute value of x raised to the k. And we have a lot of things canceling, right? These two guys cancel, the factorials cancel. So we're left with now just the limit as k goes to infinity, the absolute value of x all over k plus 1. Now it turns out that the x is not affected by the k. Okay, so the x is not affected by the k, so I can actually pull that outside and just take the limit as k goes to infinity of 1 over k plus 1, and this goes to 0. So this will be the absolute value of x times 0, which just ends up being 0. So it turns out r goes to 0 for any value of x. Okay, no matter what x I plug in, r still goes to 0. So by the ratio test, f of x converges for all, let me try this again, for all x. So what does that mean? That falls under our first category. This tells me that the radius of the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity, right? This series converges everywhere. Okay, and actually that's going to be kind of nice later on, because this is actually the approximating series for e to the x. Since it converges everywhere, it will work everywhere. Okay, but that's sort of a spoiler alert. All right, so let's look at another example where maybe it's not this simple and see what we get there. All right, let's look at our second power series here. Here we're looking at the series k going from 0 to infinity, -1 to the k times x minus 2 to the k all over 4 to the k. So in this one, I want to actually verify a couple things here. Here, our center is 2. Our ck's in each step, that's the -1 to the k all over 4 to the k. All right, so which test should we use here? Well, we could use either, probably, but notice how everything is raised to the k. So it might be prudent to use the root test, since everything is raised to the k. All right, so let's try it. Remember the root test, we look at rho, which is the limit as k goes to infinity of the kth root of the absolute value of all of our stuff. Okay, so the absolute value, that's going to cancel out all the negative things here, so we can drop that. And this whole thing we can write as that stuff raised to the k. So let me write the next step here. I'm going to write it as the kth root of the absolute value of x minus 2 raised to the k. Actually, I'm going to do it this way. And I don't know what I was trying to write there. That should be k all over 4, and this whole thing raised to the k. All right, so the kth root cancels with the k power, and we get the limit as k goes to infinity, the absolute value of x minus 2 all over 4. Now, notice our k's are gone. So since our k's are gone, this limit is just going to be x minus 2 all over 4. Now this, of course, x minus 2 absolute value. Okay, now here's how we proceed from here. So last time we actually got a number out, specifically we got 0 out. This time, however, we didn't get a number, we didn't get 0, we're still left with x's. So we need to remember, let's remember that in the root test, and this is true for the ratio test as well, but in the root test, we get convergence when rho is strictly less than 1. Okay, so when rho is strictly less than 1, well, our rho, in this case, is the absolute value of x minus 2 all over 4. So what we want is, we want this less than 1 to get convergence. All right, so this basically implies that if I were to say to move that 4 over, that we want the absolute value of x minus 2 less than 4. Okay, when you get down to here, this is our x minus a, right? X minus the center, that's our 2, is less than some number. That number is r. Okay, so the radius of convergence in this case is 4. Okay, now there are two ways you can go about finding the interval of convergence. One way is graphically. So if you're more graphically minded, you'd put your center here, which is 2, and you go out 4. So 1, 2, 3, 4, 2, 3, 4, 5, 6. So that will get you to 6, and you go out 4 this way. So this would be 1, 0, -1, -2. All right, so that will give us our initial I. I'm going to call this I star as -2 to 6. The other way you can do it is actually algebraically, where you take this x minus 2 absolute value less than 4, and you convert that to what you used to do in like algebra and pre-cal by saying, well, if your absolute value thing is trapped beneath a number, that means x minus 2 is trapped between -4 and +4. Okay, so -4 is less than x minus 2 is less than 4. Then we would add 2 to all the pieces. To get -2 is less than x, which is less than 6. Right? Which ends up giving us the same thing we got here, -2 to 6. Okay, so we know for sure that f converges in this interval, right? And it converges absolutely. So f converges absolutely in this interval. But what about the endpoints? Right? What about x equals -2 and x equals 6? Well, that we will need to check, okay? Because remember, if we plug these in, that is what gives us ones here, or yeah, that would give us equals 1, because when we put in 6 here, I'll get 4 minus 6, or sorry, 6 minus 2, which is 4, and so our rho would be 1, and if we put in -2, we get -2 minus 2, which is -4, absolute value. That gives us rho equals 1. So these values give us rho equals 1. Remember, we can get convergence or divergence when rho is equal to 1. So we actually need to check f at these values and see what happens. Okay, so let's check f at these values. Okay, so let's write f again. I spared you having to watch me write it out again. But here's the series for f. Now, let's start with 6. When we plug in 6, we're going to get, right, the series k going from 0 to infinity, -1 to the k, and then it will be 6 minus 2 all raised to the k all over 4 to the k. Okay, so we'll get k going from 0 to infinity of -1 to the k times, this will be 4 to the k all over 4 to the k, which that cancels, and now we have the series k going from 0 to infinity of -1 to the k, and we know from just previous work that this diverges. So we can ignore that. Now let's look at f of -2. Okay, so this will be the series k going from 0 to infinity, -1 to the k times -2 minus 2 to the k all over 4 to the k. Okay, so this will be the series k going from 0 to infinity, -1 to the k times -4 to the k all over 4 to the k. Now, how we deal with this is I'm going to break this piece up. So I'm going to break this up as right, -1 to the k times 4 to the k. All right, so those cancel again, and then we're left with the series -1 to the k plus k, so to the 2k, and that's always going to be positive. So that's the series k going from 0 to infinity of just +1, and that also diverges. Okay, so f does not converge on the endpoints. All right, so f does not converge on the endpoints. So I just is the open interval -2 to 6. Now you might wonder why we would ever have to check this, but it's because, remember, the rho or the r, when it equals 1, anything can happen, and that's what happens at the endpoints. At the endpoints, rho or r, whichever one you're looking at, is going to equal 1. So that is a case where you do need to check the endpoints. Okay, we'll look at an example in a bit where we might actually get convergence at the endpoints. Speaking of, that's a good enough segue as any. Let's look at another example. All right, so let's take a look at this example. It's the series k going from 1 to infinity, x minus 5 raised to the k all over the square root of k. So here, our center is 5. Our ck's are 1 over the square root of k. All right, so I'm thinking ratio test here because not everything's raised to the k. I have a square root k and something raised to the k, so I think ratio test would probably be our best bet. So we're going to look at r, which will be the limit as k goes to infinity of the absolute value of the k plus 1 step, so that would be x minus 5 to the k plus 1 all over the square root of k plus 1 times the absolute value of the k term flipped over. All right, So let's simplify this down a little bit. This will be the limit as k goes to infinity of, this will be the absolute value of x minus 5 raised to the k times the absolute value of x minus 5. Just breaking that piece down like we normally would. This will always be positive, so I can just say that that's the square root of k plus 1. Okay, here, square root of k will always be positive. And then this piece will become the absolute value of x minus 5, all raised to the k. And now we have some things canceling, specifically just these two guys here. Okay, now, in the next step, what we're left with here, the only things with k's is here. Right, the x minus 5 is no longer affected by the k's, and actually it never was, but, well, actually it was when we were raising it to the k, but this particular one is not, so we can move that outside and get that this will be the absolute value of x minus 5 times the limit as k goes to infinity, and this will be the square root of k all over the square root of k plus 1. All right, and what we can do, if it helps, we can move the limit sign in here, and this is this whole thing square root. So this will be the limit, or the square root of the limit of k all over k plus 1. And of course, this is as k goes to infinity. And so this goes to 1. Okay, so this whole thing goes to x minus 5. Okay, so what this tells me is that r is equal to the absolute value of x minus 5, and for convergence, we need this thing less than 1. Well, we actually don't have any extra work to do here, because this is already the, in terms of our x minus a less than r. So this tells me that the radius of convergence is 1. Awesome. All right, then we can manipulate this a little bit. And I'm more of a graphics person myself, so I'm going to put the center here at 5. And if the radius is 1, that means I'm going to go out 1 on each side of 5, so 6 and 4. So I'm going to call this I star is the open interval from 4 to 6. So there's the general radius or interval of convergence. So we know for a fact that f converges in this interval here. We need to check the endpoints. Because it's the endpoints are where r equals 1, and remember r equals 1 is where anything can happen. Okay, so we'll start with f of 6. Now, if we forgot what our series was, here it is. Okay, so it'll be the series k going from 1 to infinity of 6 minus 5 raised to the k all over the square root of k. So this will be the series k going from 1 to infinity of 1 to the k all over the square root of k. Well, that's just going to be the series k going from 1 to infinity of 1 over the square root of k, and this is a divergent p-series, since p is equal to 1/2. Okay, so we know that at this endpoint we have divergence. However, when we check 4. F of 4, that will be the series k going from 1 to infinity of 4 minus 5 raised to the k all over the square root of k, which will be the series k going from 1 to infinity of, this will be negative 1 raised to the k all over the square root of k. Now, at 6, we got a positive 1 of the k. That gave us 1 over root k, which is a divergent series, p-series. However, here, this is an alternating series. And not only that, it's a convergent alternating series because the non-alternating part goes to 0. So we actually get convergence. Right? F converges at x equals 4. So here on my interval, we get convergence at the leftmost endpoint, but divergence at the rightmost endpoint. So this tells me that r equals, r is 1, so that doesn't change. R, once you find r is just r. But the interval of convergence is actually 4 to 6. So closed 4 to open 6. Okay, so I can't give you a rule of thumb here that you can always apply. Like I can't say that, oh, it never, series never converge on the endpoints, or they always converge on the endpoints, or they will always converge on the left endpoint and not the right, or vice versa. It's different every time. Right? You'll have some series that will converge on the right endpoint, not the left. You'll have some series that might converge on both. You might have some series that don't converge on either. Okay, you just have to check them. It's kind of a pain, but you just have to check them. I mean, that's all there is to it. All right, so for this example, we'll have the series k going from 0 to infinity of k factorial times x minus 1 raised to the k. So since I see a factorial, I'm thinking ratio test. Okay, so for that, our r will be the limit as k goes to infinity. So we'll do the absolute value of the k plus 1 term. And actually, since there's no fraction here, well, I'll still do the reciprocal, but it will be the k plus 1 term. So it'll be k plus 1 factorial times x minus 1 to the k plus 1. And then it will be the reciprocal, so absolute value of the reciprocal, so I could really just say it's 1 over the absolute value of k factorial times x minus 1 to the k. All right, so this will be the limit as k goes to 0, or sorry, goes to infinity of, when I simplify this down a bit, it'll be k plus 1 times k factorial times the absolute value of x minus 1 raised to the k times the absolute value of x minus 1. All over k factorial times the absolute value of x minus 1 to the k. All right, so the factorials cancel, the x to the k's cancel, so then we're left with the limit as k goes to infinity of k plus 1 times the absolute value of x minus 1. Okay, so like before, we can just take that absolute value of x minus 1 out, and this will be the limit as k goes to infinity of k plus 1. Well, this, as k goes to infinity, k plus 1 definitely also goes to infinity. So r equals infinity. Well, infinity is definitely greater than 1, and this r, further, r is greater than 1 for any value of x. Okay? Except for x equals 1. Right? When x equals 1, this zeroes out before, like when we get to here, this zeroes out. Actually, I shouldn't do that because of the factorial, but when x is equal to 1, this thing goes to 0. Okay? So this means that f only converges when x is equal to 1, so the radius of convergence is 0. And the interval of convergence, well, it's really just the element 1. All right, so those are the possibilities here that you can look forward to, I guess. You'll either get it to converge everywhere, you'll get it to only converge on a balanced interval, which you will have to check the endpoints just in case, or you'll only get convergence at the center. Okay, and that's when your radius of convergence is 0. So I think that's likely enough brain melting for one video. So I will just leave it there. That should get you rolling on the homework. And in the next video, we will start talking about Taylor series specifically. And I will catch you all then. Cheers.